Test, 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 test. Okay. We're live. All right, welcome back to a new year. Hope everybody had a good vacation. I have removed the stash, as you can see. We're gonna start the year with a interesting paper here. So we have a paper here coming out of a variety of different Chinese labs here. You have ArcLab, Tencent, Shanghai Tech University, Shanghai Engineering Research Center for Intelligent Vision and Imaging, and then Shanghai Engineering Research Center of Energy Efficient and Custom AI IC. So basically a bunch of different people from the Shanghai area, it seems. Super recent paper as well, just coming out in the past week. And it's Dream3D, zero-shot text to 3D synthesis using 3D shape prior and text to image diffusion model. So this is going to be another text to 3D paper here. I think that in this case, they're going to be adding, seems like mainly the 3D shape prior, kind of as their novel contribution. The results look interesting, obviously a little weird, but you know, like for example, the lamp, the kind of the rotational symmetry on it, the weirdness of this chair. It's not quite the Iron Throne, but these are pretty good results, especially the shape and the lack of the Yanus problem, right, where there's a face on the back of the head. So let's get started here. So recent clip-guided 3D optimization methods. So, okay, CLIP is the contrastive language image pre-training model that is available under MIT license, and a lot of people use it because you can kind of use it like a data set you can train on clip embeddings. So it's kind of like a teacher-student network, and it's a lot easier to set up training where you're using clip to guide rather than find a data set for yourself. So this is more and more popular. Zero-shot text-guided 3D synthesis. So zero-shot just means you're not fine-tuning it on categories or anything else. You're just training the model and then evaluating it on your test data immediately after you trained it on kind of whatever the bulk of the data you trained it on. Although I think here they're using clip. Text-guided is just your standard using a prompt, such as a park bench overgrown with vines. And then, of course, 3D synthesis, the creation of 3D content. I think these are NERFs, neural radiance fields. So these aren't meshes with textures. These are 2D representations generated by a neural net that is trying to approximate a volume of space. Okay, so in this paper, we make the first attempt to introduce the explicit 3D shape prior to clip-guided 3D optimization methods. We first generate high-quality 3D shape from input text in the text-to-shape stage as the 3D shape prior. Okay, so basically, they have a two-stage pipeline here, where the first stage is going to be generating the 3D shape, and then they're probably going to generate the texture after that. We then utilize it as the initialization of a neural radiance field and then optimize it with a full prompt. We present a simple yet effective approach that directly bridges the text and image modalities with a powerful text-to-image diffusion model. Okay, so diffusion model. I did see this morning that Google released a paper where they do image generation without a diffusion model. So probably going to read that tomorrow, but it is interesting to see that perhaps diffusion models will be dethroned in the near future. But for now, at least when this paper was written, diffusion models were all the rage. So that makes sense that that's what they're using. To narrow the style domain gap between images synthesized by the text-to-image model and the shape renderings, we further propose to jointly optimize a learnable text prompt and fine-tune the text-to-image diffusion model for rendering style image generation. Our method, namely Dream3D, this is some ESL here, is capable of generating imaginative 3D content with better visual quality and shape accuracy than state-of-the-art methods. I mean, this is kind of subjective, but they look good to me. They were impressive enough to warrant this stream. So let's get here on the introduction. So they're just kind of motivating the use of 3D content where, right, you can use these in animations, games, virtual reality, a lot of different uses. And then they introduce the challenges here. Challenging to replicate the growth in text-to-image synthesis to text-to-3D since collecting a large-scale paired text-3D dataset is unfeasible. So this is kind of they're setting the seeds for the motivation for using basically clip guidance. Zero-shot guided 3D synthesis. Usually leverages powerful vision language models clip to eliminate the demand for paired data, right? So rather than having a data set where you have a 3D shape and then you have a text prompt that goes along with that 3D shape, you can basically just use the clip model itself, which has image encoder and a text encoder that both project into the same latent space. So then you can use contrastive losses in that latent space, right? Looking at the vector that comes out of a text embedding and then the vector that comes out of an image embedding, and then pulling them close together or pulling them apart. So there's two categories here. Clip-based generative models. Uses image as an intermediate bridge to the shape embeddings, and then switches to clip text. Okay, and then you have second method here, clip-guided 3D optimization methods. They continuously optimize the clip similarity loss between the text prompt and the rendered images of a 3D scene representation. Yeah. We'll see what that similarity loss is. It's probably cosine similarity, but maybe they have some tricks for that. First category heavily relies on 3D shape generators trained on limited 3D shapes and seldom has the capacity to adjust its shape structures. While the second category has more creative freedom with the dreaming ability to generate diverse shape structures and textures. We start to develop our method from clip-guided 3D optimization methods. Though these methods can produce impressive results, we observe that they usually fail to generate accurate and faithful 3D structures. So the actual 3D structure is difficult, right? At the end of the day, clip is trained on 2D images, and the big data sets for generative AI are really just image and text. So people are still trying to figure out ways around that in order to generate the extra third dimension, right? And it seems like the results are kind of there, but we may never get to full 3D generation until we have actual 3D data sets, but that's going to be very difficult. Due to the scratch training and random initialization, these methods tend to generate highly unconstrained adversarial content that have a high clip score but low visual quality. So, right, you're using this, I think there's a picture here. Yeah, right here. So you're feeding your text a park bench overgrown with vines into your clip text encoder and then your clip image encoder, right? And different views of your bench or your 3D object, right? So these are just different views of the same bench, and you're feeding each of these bench images into the clip image encoder. And the clip text encoder and the clip image encoder, they're taking the image and that text and they're projecting it into the same latent space. So what you really want to happen is that every picture of this bench and the resulting latent vector from that should be very, very close to the resulting latent vector from feeding this sentence in through the text encoder. So you can basically just do something like a cosine distance in between these and force the model. In this case, you would be pushing the gradients all the way back here to probably this 3D generator, such that the little embedding vectors are close together. But as clean as that kind of formulation for the training problem is, there is kind of a local minima here where you end up getting high clip scores, but the actual quality of the 3D object is low. So that's why they introduced this two-stage pipeline here, where they're first going to generate the shape, and they're going to call that the shape prior, right? So prior is just comes from the prior distribution, which in statistics, usually for a lot of real-world statistics, you will do what's called a kind of prior, which is you assume a certain shape for the distribution, usually a Gaussian, and then that will allow you to kind of do a bunch of math about, okay, if this is a Gaussian and this is what my data currently has, then blah, blah, blah. But here, prior usually refers to kind of some human assumption or some human bias that someone said, okay, we're going to assume X, and this is what they're, in this case, it's going to be this shape. So they're going to say, they're going to create this prior here, this bench, S, right? So two-stage. The texture, or the image, and then the shape separately. Okay, we then use it as the initialization of a voxel-based neural radiance field, and then optimize with the full prompt. So text to shape is itself a challenging task. I agree with that 100%. You're kind of separating it into two parts with the kind of texture and visual appearance and then shape separately, but you didn't solve the hard part, which is the shape generation. Such a design leads to mismatching problems. So they directly bridge the text and image modalities with a powerful diffusion model. Okay, so stable diffusion. Interesting that Chinese research groups are using stable diffusion and CLIP, right? CLIP comes out of OpenAI, stable diffusion comes out of Stability AI, so these are American companies. But I think the reason they're using them is because of the licensing and permitting. So if you open source your stuff, people will use it. Specifically, we adopt the text-image diffusion models, blah, blah, blah. Still suffers from the style domain gap between the images synthesized by the text and the shape renderings used. Train. We propose to address this domain gap by jointly optimizing a learnable text prompt and fine-tuning stable diffusion to obtain a stylized prompt with a stylized generator. Interesting. Okay, so one what they're doing here is they're calling this stylized prompt. So they're going to change the text itself. That's interesting. I wonder if they have a picture of that somewhere. Fine-tuning stable diffusion into a stylized generator. Okay, so we use a dataset DS contain, I think actually green is the color that we would use for definitions, containing ShapeNet renderings and text description. Okay, so here's actually where they're getting all their 3D stuff, is ShapeNet. And text in the format a class in the style of star to fine-tune the text embedding B star of a placeholder token and the weights of the diffusion model. Another dataset dreg, which contains images synthesized by the original stable diffusion with text prompts in the form a CLS, is also used for regularization. With fine-tuned stable diffusion, we can synthesize images that meet the style of ShapeNet renderings by adding a postfix in the style of to the text prompt. Okay. So this is really the key point right here, is that they're doing prompt engineering in this version of style diffusion. So they have a bunch of images from ShapeNet, which are, I think, these like images of the gray just mesh objects with a flat colored background, and they're basically telling stable diffusion that that is the actual style that they want to generate in. So they're treating a very kind of flat picture of a mesh with no texture as the style, and then they're generating images in that style, and then they're gonna probably extract the mesh from that kind of more flat style, which is a lot easier to do compared to like an actual natural image. So let's go back up here. So they make the first attempt to introduce the explicit 3D shape prior into 3D optimization, performing the corresponding while still enjoying the dreaming ability of generating diverse shape structures and textures. Therefore, they name our method Dream3D, as it has both strengths. Okay, let's get in here into the related work section. So they start with 3D shape generation. It is more challenging than 2D image generation due to the expensive 3D data collection and the complexity of 3D shapes. I think there's also a huge variety of file formats for 3D content. So the lack of a unified file format makes it very difficult to collect very large data sets, versus images have a much more standardized file format, and it's very easy to convert between image file formats, so you can collect very, very large data sets of those. Voxel grids, point clouds. Yeah, so these are different methods, different 3D formats, right? Point clouds, voxel grids, meshes, implicit fields, which is neural radiance fields. They are trained to model the distribution of shape, geometry, and texture, and a variety of other things, right? Such as emissivity, roughness, although those are usually kind of bundled into the texture itself. In comparison, some methods seek to relax the demand for direct 3D supervision and learn a 3D generator from 2D image collections. Okay, this is extensive citations here. I do like this style of citation of related work. Sometimes the related work section, people will kind of list individual papers, right? Where they'll say, this paper did this, and then they cite that paper, and then this paper did that, and then they cite that paper, and then what you end up with is just a handful of papers in the related work section. I think this is a much more high-level view of the 3D shape generation literature, where they give you the general themes, and then they kind of just put 10 different citations here. So I think this is cleaner, it's less verbose, and it at the end of the day, they're giving you the 50 different papers that you need anyways. Okay, so next section of related work here, we have text-to-image models. So again, they reference GANs, although GANs are kind of not really used anymore, but GANs were some of the first models that did this kind of freeform generation. DALL-E as the first one there, CogView, Glide, Clip, DALL-E 2, which was the diffusion model, leverages a diffusion prior network to translate clip text embeddings to clip image embeddings. That's largely what this paper is doing as well, but in the 3D space. ImageGen and Stable Diffusion utilize a large pre-trained language model to guide the sampling process of a diffusion model in pixel space and vector quantized discrete latent space. Yeah, so this is another theme that we've seen in these papers again, where with these diffusion models you can either choose to add and remove the noise directly in the pixel space or in the latent space of the model itself, where the latent space noise, or the diffusion in the latent space, is faster and more compute efficient, but diffusion in the pixel space, I think they get slightly better results. I don't quite remember what the TLDR for that was. Okay, now you have zero-shot text to 3D. Yeah, so text to 3D methods leverage the joint text image modeling ability of pre-trained language models, e.g. Clip, to eliminate the demand for paired text 3D data, which is hard to acquire. Okay, so ClipForge trains a normalizing flow model to translate clip image embeddings to a VAE shape embeddings, which replace clip image embeddings with text embeddings at the inference phase to generate shapes. VAE is variational autoencoder, and a popular version of that was the vector quantized version of that, where basically you replace the embedding with a code book that's quantized. To close the gap between the text and shape modality, a fresh work named ISS trains a mapper to map the clip image embeddings to the shape latent feature of a pre-trained single view reconstruction network. Greenfields and ClipMesh are pioneering work that explores zero-shot 3D content with only clip guidance. Pure Clip Nerf further improves Dreamfields with grid-based representation and more diverse image augmentation. So Dreamfusion has gained a lot of popularity with its impressive results. Powered by a pre-trained 2D text-to-image model, it can generate high-fidelity, relightable 3D objects. So the relightable part is interesting too, right? Where in these nerfs, the lighting is actually baked in, right? It's part of, it's kind of just part of the scene, right? There's a specific kind of angle that the lighting is coming from, and then there is no way to kind of separate that out. So I think in the future you'll continue to see kind of, maybe it'll be a separate model, but like a model that can kind of disentangle the lighting direction in the nerf. 3. Given an input text prompt Y, we aim to generate 3D content consistent with the description of Y. Okay, so we're going into the definitions and math here. So let's take out our green highlighter. We're going to have a input text prompt Y. consists of two stages. So first stage, we acquire an explicit 3D shape prior S with a text-guided 3D shape generation process. This is split into a text-to-image phase using fine-tuned stable diffusion model GI, so generative model I, and an image-to-shape phase using a shape embedding mapping network GM, together with a high-quality 3D shape generator GS. So there's three different models here: GI, GM, and GS. We leverage the 3D prior S to initialize a neural radiance field and optimize it with clip guidance to obtain the final 3D content. Our framework only requires a collection of untextured 3D shapes Si equals 1 to n, so the set, without any text labels for training the 3D generator GS, and the fine-tuning of process of GI converges very fast. So the shape generator GS, I think this is, we saw the image here. So this is how they're training the shape model. Is they're basically just rendering this collection of untextured 3D meshes as if it was a style of 2D image, and then using stable diffusion to generate in that style, which is kind of interesting. That's how they're getting this 3D shape generator. So the only, apart from clip, which is of course kind of like a way to get to a large paired text and image space or data set, they have an actual data set of untextured 3D shapes. So this is kind of really the only external data set they're using, and then the rest of their models, they're kind of relying on the pre-trained stable diffusion model and then the pre-trained clip model. Which is, I think, interesting, and as you move into the future here, like training from scratch on massive data sets is very expensive and very difficult. So more and more you're going to see people just simply use these big foundational models as effectively synthetic data generators for their purpose, right? Which is what you're seeing here. It's using more powerful AIs to train application-specific AIs. I think that's a trend that you're just going to continue to see. Okay. 3D optimization with clip guidance. So clip is a powerful vision language model consisting of a text encoder, E of T, and an image encoder, E sub I. By maximizing the cosine similarity, so that's what we guessed was the loss function that they were using to compare the two latent vectors there. So the cosine similarity between the text embedding and the image embedding, encoded by E sub T and E sub I, explicitly on a large scale paired text-image training data set. Clip aligns the text and image modalities in a shared latent embedding space. Previous work leverages the power of a clip to synthesize 3D content, starting from a randomly initialized 3D representation parameterized by theta. They render images from multiple viewpoints and optimize theta by minimizing the clip similarity loss between the rendered image and the text prompt. Okay, so you have a couple different terms here. You have your actual rendered image, R, which is a function of V sub I and theta, where V sub I denotes the rendering viewpoint at the ith optimization step. So you have your 3D object and you're taking a variety of pictures from a variety of viewpoints of this object. And you want the, whenever you feed this image into the encoder, for the clip encoder that takes in that image, you want that vector, right? And then this transpose here, you're basically doing a cross, right? So there's the dot product, and then there's the cross product here. You're doing the cross product of that and the text embedding with your text prompt. And if you take the cross product of those, right, you're going to get, if they're orthogonal, you're going to get a different thing than if they're right on top of each other, right? So the dot product and the cross product are just kind of ways of measuring how orthogonal two vectors are. And an embedding in a latent space is a vector. And that's going to effectively be your loss, right? And the negative here just means that you're trying to make this, you're always trying to decrease the loss. So that's why they put this negative there. Okay, so adopt neural radiance field nerf as a 3D representation theta. So theta here is the parameters of a neural network that represents that mesh. In this case, represents that 3D object, which is a nerf. If you were using textures and meshes, then theta would be the image for the mesh, the points in the mesh, and so on. Not that anybody actually would use that in this case. You couldn't actually substitute it in because you can't push gradients through a texture and a mesh representation, but you can push gradients through a nerf representation, which is why it's a learnable representation, which is why the future of 3D content is all nerfs. Okay. So then they have kind of a little caveat here on if you just do this naively, you're going to fail to generate accurate and detailed 3D structures. So we utilize those methods to stylize the 3D contents with text prompts that contain common objects. Results show distortion artifacts and look a bit strange. Okay. So here are the reasons for these failures. So they say the first reason for this failure is the optimization process starts from a randomized 3D representation without any explicit 3D shape prior. Thus, the models need to reimagine the scene from scratch, which is very challenging. Yeah, so you don't really have any shape prior. The clip loss in equation concentrates more on the global consistency between the rendered image and the text prompt and cannot provide strong and precise supervision on the synthesized 3D structure. Yeah, so there was another paper that we read last year, a couple streams ago, where they dealt with this as well, right? Where the clip loss is will enforce global similarity, but the individual little parts of the image aren't as good. So what they did in that other paper is they actually did these patches. So they would break up the image into smaller patches and then do a clip loss on each individual little patch, and then have a clip loss on the whole image globally, so that globally the image is like semantically consistent, and then each individual patch of the image is also semantically consistent. So that's something that this paper could do as well, where they have kind of this pyramid style, like whole image, and then a grainier version of that, and then cut different sub images within that, right? The patch kind of approach. I don't think they actually do that in this paper, though. They're just going to do this two-stage optimization with 3D shape prior. To overcome the aforementioned problem and synthesize more faithful 3D content, we propose to adopt a text-guided shape synthesis process to produce a high-quality 3D shape S from the input text prompt Y. Okay, so they're going to make this shape S first. We don't really know what that shape means right now. We first synthesize a park bench 3D shape without textures. So this is the nerf that they use, DVGo. I haven't heard of that particular type of nerf, but I assume it's just your kind of standard nerf. So you have a voxel grid, V density, and this voxel grid is three-dimensional here. You have however many x dimensions, however many y dimensions, however many z dimensions, and you multiply all three of those out, and that's all real numbers in that. So this is just kind of telling you the dimensionality of the voxel grid space. Then you have a shallow MLP framework, FRGB, for color prediction. So this is the actual network inside the nerf that takes the viewpoint that you're looking at, and then maybe some other things, where along the ray that comes out from that viewpoint you are, and maybe where along the actual voxel you are, and then it'll actually output the color. So RGB is the final pixel color that is produced there. Given a 3D shape, it's an SDF grid, so this is the signed distance function here. So also the same dimensionality as the voxel grid density function. Signed distance function, signed, it just means it's both positive and negative depending on whether you are inside the boundaries of an object or outside the boundaries of an object, right? It just basically tells you how far away you are from the boundary of an object in 3D. This is the density function here. You have 1 over beta sigmoid. Let's get some images just so you guys can see. So a sigmoid looks like this, right? So the sigmoid, if it's very, very large negative number, it'll be 0, and if it's a very, very large positive number, it'll be 1. So it basically just squashes your input into 0 to 1 range. So the 1 over beta here is just a hyperparameter. So beta is a hyperparameter here, controlling the sharpness of the shape boundary, and smaller beta leads to a sharper shape boundary. So really they're just squashing the signed distance function to between 0 and 1. And then that is this capital sigma here, and then they're doing the inverse soft plus. That's what that looks like. Soft plus, you can see here, it goes, this is not the inverse. Let's see if we can find the inverse soft plus. Okay, we're not going to find it, but it's basically a similar kind of idea, right? Where you're taking your input, and if your input is very, very large in the negative dimension, it'll just squash it to 0. But if your input is very large in the positive dimension, it won't squash it to 0. So this is another kind of squashing you can see there. And then they max, right? So then they say the max of 0 or the soft plus. And what that does is that if it's very, very large and positive, it'll just, when you put it through this max function, it'll always be 0. So this is only going to allow negative numbers. It's only going to be negative numbers. Anything that is positive will be squashed to 0. So the purpose of that is that anything that's inside the shape boundary, right? Anything that's inside would have a positive signed distance function value. But if it's positive, if it's inside the object, you're not going to see it anyways at the very end. So you just get rid of it, and you just say, okay, it's at the 0. Any point that's within the boundary of the object, just 0 it out and make it the actual boundary of the object. So you don't spend any time trying to figure out what points inside the object look like. Okay, so they set beta equals 0.05. We follow the practice of DVGO and adopt this representation for the density voxel grid. We clamp the minimum density value of outside the shape prior as 0 to ensure the distribution of the accumulated transmittance is the same as DVGO. Okay, let's actually DVGO voxel neural radiance. So this is the actual paper that they use. Super fast convergence for neural radiance field reconstruction. So just seems like motivation. NERF, excellent quality and flexibility, very slow due to MLP queries, replacing the MLP with a voxel grid. Previous works have shown large inference time. Okay, so it's basically a NERF, but they're doing some tricky stuff with the voxel to make it render faster. And a lot of voxel just basically means you take your kind of your cube of space that your NERF is representing, and you cut it up into little subcubes, right? And each of those little subcubes is called a voxel. And a lot of the speed and compute and efficiency optimizations for NERF are based around the idea that a lot of that little cube of space is actually empty, right? So the density in that little cube is 0, which means that anytime you're in a little part of that or you're in a little voxel that is going to be empty, you can just not compute that and just save the compute for that. So most 3D shape generation based around voxel, the optimization is based around this assumption that in 3D space, most of it is empty, you know? Okay, so they clamp the minimum density function outside the shape prior to ensure the distribution of the accumulated transmittance. Okay. So now that they have this density grid V density initialized by the explicit 3D shape S and the color MLP F RGB, this is the actual NERF here, they can actually render the images. So this is their rendering function, right? It's they introduced it here as well, but here they're more explicit about what goes in, where you have your viewpoint V sub I, you have your FRGB, which is your multi-layer perceptron, and you have your V density, which is this here. It's the combination of the sign distance function from this DVGO paper. We perform background augmentations for the rendered images and leverage transmittance loss introduced by 25 to reduce noise. Okay. So background augmentation, I think that refers to the like color of the background here. So you can see how in this here the kind of 3D shape style that they're asking Stable Diffusion to generate. It has a flat background color, which means you can remove that background and probably just replace it with, I don't know, something like ImageNet or random noise, and then that'll give you a method of data augmentation that should ultimately give you more, allow you to train for more epochs without overfitting. So we also adopt a shape prior preserving loss to preserve the global structure of the 3D shape prior. Okay, so they have an additional loss here where they have this script 1 is the indicator function, and alpha is a function that transforms the density into the opacity. So opacity is just how see-through something is. So neural radiance fields, in addition to neural radiance, the multi-layer perceptron in a neural radiance field, it usually here in this case predicts the color RGB, but it can also predict the opacity, right, the see-throughness of a point in space. So they have this function here that transforms the density of the signed distance function into an opacity. And if the opacity is above a certain threshold, then you can say that any point you sample along the ray that comes out of that viewpoint is no longer worth sampling into, or is no longer worth calculating, because the opacity of previous points is high enough that you wouldn't be able to see through them anyways. So that's this alpha here of the density, and then you have the signed distance function less than 0. What is the indicator function? This is probably just a stepwise. Indicator function of a subset of a set is a function that maps elements of the subset to 1 and all other elements to 0. Yeah, so it's basically just a step function. So anywhere where the signed distance function is less than 0, it'll probably set it to 1, and then anywhere where it's greater than 0, it'll set it to 0. So it's very similar to this operation here that's happening with the soft plus. And all of this gets packaged together. You sum it over every single XYZ point within the voxel, or I guess every single voxel, and then that's your loss that they're saying here, this loss prior. My nose is so itchy. Alright, by initializing the nerf representation with the explicit 3D shape prior, we give extra knowledge on how the 3D content should look like and prevent model from imagining from scratch. Okay, 3.2 here, section 3.2, stable diffusion assisted text-to-shape generation as 3D shape prior. So to acquire 3D shape priors, we require a text-guided shape generation scheme. Text-to-shape is inherently a challenging task due to the lack of large paired text image datasets. Yeah, and that really makes me wonder if it's ever going to be solved, right? Are we ever going to have a very, very large text-to-shape data set? Probably not. I think that we're going to be using these kind of the only text and image data sets that we have that are very big are the just text to 2D image. And then I think that the way that we're going to get 3D object generation is basically through what this paper is doing, like clever ways of using text to image pre-trained models or text to image data sets in order to get the actual 3D shape. This is kind of an over-engineered approach, I think, like using the stable diffusion to generate these like kind of stylized pictures and then doing background augmentation on it. Like, I think that's a little bit too complicated. I think a simpler version will come up, and somebody will come up with a simpler version to do this, but I think leveraging things like clip and stable diffusion is how people are going to ultimately get 3D content or 3D generation with these AIs. Happy New Year. Happy New Year. Welcome back to the stream. Okay. Clip Forge trains a volumetric shape. Test time, it replaces the image embeddings with clip text embeddings. ISS, this is almost like a related work section here. Trains a mapper network to map the clip image embeddings of shape renderings to the latent space of a pre-trained single view reconstruction model. Different from the aforementioned approaches, which connect the text and image modalities in clip embedding space, we use a powerful text-to-image diffusion model to bridge the two modalities directly. So this is where they're going to bring in stable diffusion here. We adopt a text-to-image diffusion model to synthesize an image from the input text prompt, and then feed the image into an image-to-shape module to directly generate high-quality 3D shapes. We introduce a new novel technique to alleviate this gap. Okay. So text-to-image diffusion models. This is going to just basically be the background on diffusion models here. So the way that diffusion models work is you have a data distribution X naught, or data distribution Q, and the X naught is a sample from that data distribution. You are adding Gaussian noise in, and you're basically adding this noise and removing this noise in a series of capital T time steps, right? And T can be anywhere from just one time step to thousands of time steps. So the sample from the data distribution, and again, this sample is going to either be the actual pixels or it's going to be a latent vector, is comes from the previous image, right? So x at t minus 1 plus this noise here. So sigma, lower sigma t minus 1 denotes the noise added at time step t minus 1, and here alpha t is the noise level, so kind of like a scheduling, right? Like you would do learning rate scheduling, here you're doing noise scheduling, and as you go closer to time capital T, you're going to have either more noise or less noise. A neural network sigma theta, or epsilon theta, is trained to reverse the diffusion process by estimating the added noise at each time step. At inference time, we sample from the diffusion model iteratively through a sampler. Text-to-image diffusion models are conditional diffusion models. Given the text prompt Y and let C naught denote a text encoder that maps Y into a conditioning vector. The training objective of text-to-image diffusion models is written as this. Okay. So this is the loss for a diffusion model, and it's the expected value. Here, this is these two parallel bars here, and the squared, that just means the squared difference between these two things. So it's like you take these two numbers, you take the absolute value, and then you square them. So it's going to penalize large differences much more than small differences. That's what that squared does. L2 loss is another way to describe that. And these two terms here are E sub t, which is the noise added here. Epsilon t. And then you're going to have epsilon theta, which is the noise predicted. So, right, the neural network is trying to estimate the noise. And the neural network that estimates the noise, what it's receiving is the image at time t, or the latent vector at time t, the current time t, and which is also from 0 to 1 usually normalized, and then c sub theta of y. So y is your text embedding, in this case the text prompt, and you're feeding it into a text encoder to get a, what they call here, the conditioning vector. And like in other diffusion models, there's a lot of different stuff people do with this conditioning here, right? So you can condition it on the class, you can condition it on text. Sometimes they condition it on both some vector and then also a null vector, and then combine those in a way with a hyperparameter. So there's a variety of different ways to use or condition this neural network that predicts the noise when you're training a diffusion model. So in this work, we use an open source text-to-image diffusion model, i.e. Stable Diffusion. Stable Diffusion, okay, so this is the actual one that they use here. And actually, if we actually go here, let's go to comp viz, Stable Diffusion. Yeah, so this one's actually interesting. They might have changed this license. Yeah, so I mean, this is, they've expanded this, right? So now Stable Diffusion is not necessarily safe to use anymore. This is not MIT license. This is not use and do whatever you want with it. Their license, which they put in here, August 22nd, 2022, is now relatively complicated, and there's all kinds of caveats here. Generate personal identifiable information, fully automated decision making, blah blah blah. So like these use restrictions are so broad, and they're designed to be very broad. And the reason they do that is so that basically if they ever want to sue you, they can sue you and say that you're violating these, right? So provide medical advice or medical result interpretation, like anything can be kind of that, right? So I don't know. I would steer away from using Stable Diffusion for that. And a lot of times people will use real issues with AIs, right? You can use AIs to generate content that is not great and that is bad and that you wouldn't want to generate, but they use that as an excuse to basically have full control over who gets to use the AI model and who does not. And I think that's going to be a theme as we continue to go through the 2020s, where basically bad content is kind of used as a justification for full control over these. So for your projects, if you're using these different things, especially if you're trying to maybe do a startup with this project, right, and eventually kind of make money with this startup, you're going to be very careful about using things like Stable Diffusion, because if you ever compete with them, or if you're ever in a position where now you're threatening their market, they will figure out some way to use their licensing to force you to stop. So things like Clip, totally fine, MIT license. Things like Stable Diffusion, much more dicey, right? And if you start messing with their ability to make money, they'll figure out a way to sue you. So you have to be careful. Okay. Stable Diffusion utilizes a clip VIT large 14. So this is a vision transformer. Specifically, like there's different sizes. I think this is the large one, and then 14 just means that they're cutting the image into 14 little patches and then feeding each of those patches into a transformer, which originally being designed for sentences requires a sequence. And it's trained on the Leon 5B dataset. High-quality 3D generators. So high-quality 3D shapes are highly desired, and more precise 3D geometric shapes can provide a better initialization for optimization. ClipForge utilizes a volumetric shape autoencoder, which has difficulty in generating plausible 3D shapes. To provide high-quality 3D priors, we adopt a state-of-the-art 3D generative model architecture, aka SDF style GAN, that maps a random noise Z to a latent shape embedding E sub s, which is in the set of W. You don't know what that W is. Why is my nose so itchy? Okay, M9 question here. That's a good point, to check the licenses before you get too far into using it. But if you use an earlier version, does the earlier license apply? Not sure, but I think the way the licenses are written now, they forbid the use of previous model versions. And so I think that they know that that's a problem, right? So like they released the Stable Diffusion 1.4, and that one had a very permissive license. So people were using it for kind of all their startup ideas, and then Stable Diffusion was like, oh wait, this is a huge problem. Everybody's just using our model for their own ideas. We have no control over this. So I think that what they did is that more recent licenses for Stable Diffusion 2, for example, they said, okay, one of the things that we're going to do is we're going to make using previous versions of our model illegal, so that you can't use previous versions. So I don't think it's all settled yet. I think that you're going to see probably a couple big court cases that very slowly go through the different jurisdictions, like America and Europe, right? They're all going to have slightly different interpretations of this, but I don't have high hopes for it, right? I don't think that we're going to come into, for example, 2025. I don't think in 2025 you're going to have all these models under MIT license. I think that's probably not going to be the situation. You're probably going to end up in a world where all these models are very tightly licensed and you can't use them for any kind of startup or anything without paying them money, right? So they'll figure out a way so that it's very difficult to have your own idea or use it for your own purposes without giving them a bunch of money. is the way that it works. Okay, so feeding the interpolated into an X jointly trained MLP network. Ooh. Different from the original SDF style GAN that trains one network from the shape, we improve it to chain one shape generator GS on 13 categories of the ShapeNet dataset. Okay, so this is the data set that they're using to train this the shape prior, but it kind of sucks, right? Because this ShapeNet data set only has 13 categories, and I think actually if you go up now, it makes sense. They probably have, right, like cars, chairs, TVs, like these are kind of 3D shapes that are limited to the categories of existing 3D data sets. So despite the fact that they kind of talk about the lack of 3D data sets and what that does to the ultimate 3D generation models, they are also limited by the same thing, right? They separated out the shape, they separated out their pipeline into these two parts where you have the shape stuff and then you have the more texture image stuff, but the shape prior is limited by the ShapeNet dataset. So shape embedding mapping network. To bridge the image and shape modalities, we further train a shape embedding mapping network, GM. We first use GS to generate, in general, you mean the industry will want to make money if you use their stuff for business, but it's still open source for personal. Maybe. I think what they don't want is for you to have the model and run it on your own GPU. To use the model and run it on their own GPUs. They want startups to pay them every time the model gets run. Similar to AWS. So companies pay AWS in a way that scales with the compute. So the bigger your company, the more you pay AWS. These models will be monetized in a similar way. Right, because if they just made it open source, then you would be able to take that model, fine tune it for your application, and then just run it on your own GPU, right? And then OpenAI would get no money from that. You would just be running that model on AWS hardware, and you'd be paying AWS for the compute, but OpenAI wouldn't see any of that. So what OpenAI wants is basically that every time you use their model, you pay them like 1 cent, right? So that if your startup ever gets big and you have millions of users using your services, they would be getting 1 cent every time that you run their model. So like they really want a monetization model that's like per use. And part of that means that you can't use their model. But again, like all of this is still speculation, right? It's like we don't really know what this is going to look like. And maybe the court systems and the judicial systems of the different countries decide that, hey, actually someone using your model architecture is totally fine, and you can't say that you have some kind of license on that specific idea, so therefore anybody can use a diffusion model. So, and then different countries will have different versions of that regulation. So you could see something super interesting where some countries are super permissive, and then everybody puts their data set, their data centers there. It's interesting, and I don't really know how it's all going to work out. Okay, then we render each shape from K viewpoints to obtain shape renderings. And then they have this shape embeddings. The dimensionality of that shape embedding is E. And then they transform those shape embeddings into image embeddings. Finally, they use this data set to train a conditional diffusion model, which can synthesize shape embeddings. Okay, interesting. So they have a diffusion model that directly generates in this shape embedding space that they created here. So to prepare the data set, we generate 64,000 shapes and render 24 views for each shape. This should actually be blue. That should also be blue. With azimuth angles in the range of -90, 90, and elevation angles in the range of 20 to 30. So this is a pretty limited range for the azimuth, which is this one, right? Or elevation, sorry. So they're rendering the object from -90 to 90, so it's something like this. It's like 180 degrees. But then the elevation is more like this. It's very limited. Use Stable Diffusion to directly bridge the image and text modalities. However, image to shape is trained on shape renderings, which have a large style domain gap from the image synthesized by Stable Diffusion. Inspired by recent work on controllable text-to-image synthesis and Dream Booth, we propose okay. Hello. I do not know how to say your name. I'm sorry. I'm an undergraduate student who is interested in AI. I'm reading the textbook of Murphy, and it takes many months. I'm so worried because I feel so outdated in this fast field. Do you recommend reading some textbook that can give mathematical insight, or reviewing new papers and implementing them instead? Don't worry too much about the book-content. Just focus on consistency, and you will eventually learn what you need. Yeah, so I mean, it's not, I think with a lot of things, especially learning, it's like you don't need to worry about a specific content. It's not like one deep learning book is better than a different deep learning book, or one paper is better than a different paper. I think it's more about just progress over time. I think if you just try to do it every day, like every day try to read a little bit, every day try to do a little bit of coding, and then a couple years of that, and you'll eventually become quite good at that. So it's more about consistency and reading every day than it is necessarily about reading the right things. So don't worry about, am I reading the right thing? Am I not reading the right thing? Is there some other book I should be reading? Just kind of keep reading and keep consuming content, and over time you will learn what you need to learn. Hope that was useful. Core idea, synthesize image. Then we can seamlessly feed the generated stylized images in the image to shape module without suffering from the domain gap. Okay, we're almost done here with this section. Let's power through here. The fine-tuning process shown in Figure 8 to fine-tune Stable Diffusion. So Figure 8. Damn, that's quite down. What do we got here? Figure 8, Figure 6. Figure 8 is all the way down here in the appendices. All right, Figure 7 and then Figure 8 here. So the result of fine-tuning Stable Diffusion using shape renderings with different backgrounds. For each type of background, we visualize the shape renderings used by fine-tuned Stable Diffusion on the left and the images synthesized by the fine-tuned Stable Diffusion on the right. Okay, so they were using Stable Diffusion to generate these images, and they basically used prompt engineering to make images that were in this style, right? And this style is ultimately based on a data set from a paper called ShapeNet, which has 13 categories. I think it's like boat, car, chair, airplane. That's why all of these are boats, cars, chairs, airplanes, and there's basically only a limited set of those. And because these are very kind of object-centric and standardized, you can basically augment them by changing the background, and that's what they're doing here. These actually seem a little bit primitive. Like, I think they could have gotten better results by, rather than just using a solid color, using random crops from a real-world image data set, such as Coco or ImageNet or something like that. I think in that situation, the variety in the background would have been a little bit more interesting, and they could have maybe gotten a little bit more performance from it, but this is also fine. Okay, so while we're here, let's look at this Figure 7, the network architecture of the 3D generator based on SDF style GAN. Thanks, your video papers are so good. I appreciate that. Okay, so you're feeding here, this is the random noise vector. You're feeding the noise. You get this E sub S, I don't know what that is. Then you feed that through the generator, you get F sub V. You get X, you interpolate between that, put that into the multi-layer perceptron. I think this might be the GAN. Is that what this is? Or not the GAN, the nerve. Local discriminator, real discriminator. 3D generator based on style GAN. Okay, I don't know what that is. I think that's the last part that we haven't read yet. We'll see. Okay, let's come back to here. So okay, we were here where they mentioned figure 8. Yep. We need a data set of shape renderings for each shape S in the ShapeNet data set. We render a set of shape renderings. Okay, so this is the different shapes. For each rendering I sub S sup J, we associate it with the stylized text prompt Y sub SJ in the format class in the style of star. So this is the prompt engineering that I was saying, where basically kind of the same way that you would use image augmentations, where you like crop out and then you substitute the background. People are starting to now have that same concept but applied to sentences, where you have some specific sentence structure, such as here a blank in the style of blank, and then you replace those blanks with different things in training. So here class is replaced by the shape category name and star is a placeholder token. So I think this is kind of super cool, where people are starting to take some of the concepts and ideas out of like image augmentation that have been around for a very long time and start applying them to prompts for when using these image text pre-trained models as part of their training pipeline. For example, for an image rendered in a chair shape, the associated text, a prompt is a chair in the style of X. We use a paired data set to fine-tune stable diffusion. During fine-tuning, we freeze the clip's text encoder. Yeah, I mean, you wouldn't necessarily want to push gradients down that. The clip text encoder is already good enough. You don't need to fine-tune it for this specific application. The parameters theta of the diffusion model. Again, this diffusion model is predicting the noise. By optimizing the text embedding, we aim to learn a virtual world that is not in the vocabulary of the text encoder, but can best describe the style of the rendered images. Okay, so they are doing this for 2,000 optimization steps, which takes 40 minutes on a Tesla A100. So, I mean, Tesla A100 is still a relatively expensive GPU. Yeah, so it's like a $30,000 GPU, but 40 minutes is pretty fast. Fine-tuning stable diffusion using shape renderings with a pure white background would result in a chaotic and uncontrollable background during inference, while augmenting the shape renderings with a random solid color background can make the fine-tuned model synthesize images with solid color backgrounds stably. Thus, we remove the black background easily if needed. Okay. Okay, so now we're in the experiment section here. So, experiment, and then we're almost there. In this section, we evaluate the effectiveness of our proposed text-guided 3D synthesis framework. We first compare our text-guided 3D synthesis and results with state-of-the-art methods. Okay, so the data set, so they have the ShapeNet, right, which has its 13 categories. And they use the data pre-processing to produce 128 to the third SDF grids from the raw meshes. So they're basically taking these 3D boats and chairs and cars, and then they're basically taking different views from them. And that's how they're generating the 3D stuff. So this is synthetic data generation here. And they're also using these not only for the images, but also for the SDF grids, so signed distance function grids that they're going to use for the shape prior model part of their pipeline. 3D generator G of S adopts architecture of SDF StyleGAN, and the diffusion model embedding MatWork GM is based on open source DALL-E 2. Okay, interesting. So they're using this one. Star that. Implementation of DALL-E 2, OpenAI's updated text-to-image synthesis neural network in PyTorch. This is pretty cool. MIT license, nice. Pre-trained. This is really cool. Yeah, you have little UNet coder. You can actually like call the different parts here. They have DALL-E 2. They have Clip. This is badass. We should totally look at this. Reference all their stuff. I mean, I don't know what this MIT license here means. Like at the end of the day, like you're gonna get sued by OpenAI if they want to sue you, but this is pretty cool. They have a little Discord too. Lucid Rains. San Francisco, Lucid Rains, GitHub. This is the guy, Phil Wang. Cool. This guy pumps. Look at this. Look at this commit history. This guy is insane. It's very impressive. Okay. How does that 40 minutes translate to running it on a 3080 RTX? So the amount of memory is huge, is a big difference, right? So NVIDIA A100. Yeah, so NVIDIA A100 has 80 gigabytes versus a 3080 has 10 gigabytes, right? So 80 gigabytes on the A100 versus something like 10 gigabytes on the 3080, maybe more or less. Like there's different versions of these cards that have more or less. So if you think about it, if you have a big model that takes up all of the memory, right? All 80 gigs of memory, you can perform one inference in the A100 that takes 8 inferences in the 3080, right? You'd have to, and not only is it 8 inferences in the 3080, but it's 8 inferences where you have to basically take everything out of the memory, put everything new in the memory, right? Every time you load a model onto the memory or load a batch onto the memory of the GPU, that's actually one of the more costly things to do, is basically loading the memory, unloading the memory. So the thing with these big GPUs is it's not that the clock speed is higher. At the end of the day, the clock speed is probably about the same in both of these. It's the memory that really allows you to train big models much quicker because you don't have to constantly load and unload different parts of that model. So I think if you're using a small model, right? So if you were using the VIT like VIT small, right? the smallest version of a transformer and training it on small batches, you could train it on this 3080, but with these big GPUs, you can use the very big versions of the models that don't even fit on the smaller graphics cards. So it's not just kind of a speed thing, it's also the big GPUs are cheaper to use, or are not cheaper to use, are easier, much easier to use if you're training big models. So you probably can't train the big model they use on a 3080 without extra work. Train the shape embedding mapping network. They use this one, so this one's actually huge. Clip VITB32. Like, let's, if you go clip VITB32, I just want to see how big this one is. It's got to say it somewhere, right? They don't tell you how big it is. Maybe it's here in the actual paper. Clip VITB32 model size. Come on, just tell me. Somewhere on here they have to tell you the model size of this one. Okay, here you go, benchmark. Benchmark papers are good because they'll tell you the actual size here. Apparently this benchmark paper's crap. Okay, maybe here, maybe on the actual clip, they'll tell you the different size. Oh. Model card. Model versions. Yeah, okay, we can't find this. Sorry, guys. But I think this is the bigger one. VITB32, I think, is the biggest one. Okay. There's stylized text to image, so this is actually the 1.4 stable diffusion, which I think is actually the first one. So this is like the original one that was like released by Stability AI and their big kind of like release party, if you want to think of it that way. Okay, the learning rates here, so this is a big learning rate for the density, small learning rate, kind of standard learning rate for the color prediction. 5,000 steps. My favorite metric for quality, Frichet inception distance. If you've listened to previous streams, you've heard me disparage this particular quality metric here because I just think it's not a good quality metric. Fields, okay. They compare to 3 different things here. They compare to Dreamfield, Clip Mesh, and Pure Clip Nerf. So these are 3 different kind of, I guess, nerf generators. Maybe Clip Mesh actually gives you a mesh, but ultimately what they're comparing is the 2D images that result from this 3D generation. Right, so all 3 of those methods are going to generate, here we go. They're going to generate a 3D object, usually in nerf format. In this case, it's a mesh, but in these are nerfs. And then they're going to render it from different views. So these are different views of the same text prompt being fed into different 3D synthesizing models. So, I mean, these are obviously picked. These are hand-picked or cherry-picked, as it's sometimes called, in order to kind of show the results. But I think one thing that you see here is kind of the semantic information I feel like is a little bit better. Like, for example here, a table for playing foosball. Like, the Dream3D, which is this paper, has very good shape, right? You look at this, it has actual 3, or it actually has legs on the chair, versus here you don't really have the concept of legs here. This is just a blur of crap, and then here it actually just looks like a football, like an actual ball. So it seems like really the strength of this paper, the Dream3D, is kind of the explicit shape step does lead to much more semantically correct shapes. Right, so their 3D shape prior really is good. All the baseline methods and ours leverage the VIT16 encoder for optimization. Thanks to the 3D shape prior, our method starts the optimization from a better point, thus alleviating the adversarial generation problem that focuses on obtaining a high score for the guidance clip model. Qualitative results, I think they beat them on that. I think that's good. Research on zero-shot text to shape is still limited. So we first synthesized 3 shapes for each prompt for a dataset consisting of 233 text prompts provided by ClipForge, and then render 5 images for each shape. Really, is it just generating half the shape and mirroring it to get the rest of the other side? I'm not sure. I think it's generating a shape embedding, and then that embedding is being, you can render it from different sizes here. All of these are symmetrical, so I see what you're saying, where maybe they can just generate half of it and then mirror it to the other side, but it doesn't look like that's what it's doing, right? Like, you can actually see that here, like right, this side here, the mesh for this is different from the mesh here, so I don't think it's doing like a symmetry kind of like copy thing, although that's really what they could do. They could do that for all these shapes, like chairs and cars and planes are all bilaterally symmetric, so they could do that. That's actually a good idea. All the visualized meshes are extracted at the resolution of 64 to the third. So this here, this resolution that you see here, like that basically is just that means that the little volume is a voxel, is voxelized, and then each each XYZ dimension has 64 different possible cubes. So there's 64 by 64 by 64 individual voxels inside this larger volume. Yeah, so this table here, what they're showing you is that this is the bigger clip model, and then this is the smaller clip model. So what they're showing you is that their version here actually doesn't have as big of a difference. So some of these, such as dream fields, like if you're using the small model here versus the big model, it makes it more of a difference. Maybe this is not the model. Maybe this is the number of patches. Clip VIT 16. That's not what I wanted. Model size. God damn. Let's go on the blog post. 16. Okay, no, so actually the 32 one is actually smaller. Yeah, so B32 is smaller than B16. Right? Forward pass gigaflops per image. So this is how much compute the B32 model is doing, and you can see it's right around here. It's about as much as the ResNet 50, right? And then B16 is actually much bigger than that. It's actually bigger than, for example, the ResNet 152. So I'm comparing them on the x-axis here, which is the forward pass gigaflops. So that's actually interesting. My mistake there. So this is actually the bigger model. VITB16 is the bigger one. VITB32 is the smaller model. We achieve a lower FID than ClipForge. Forge leverages a volumetric which suffers from poop shape generation capability. I think they meant poor. I'm going to screenshot that. All right, let's go into their code here. Okay, they haven't actually put a GitHub repo for this yet, but I would have totally told them that they mistyped it here. It should be poor. All right, ovulation studies. So the effectiveness of fine-tuning on Stable Diffusion. We use the original Stable Diffusion model and then use these images to generate 3D shapes with the image to shape module. Strategy would degrade. Okay, so table 5. It's all the way down. We'll skip it for now. The effectiveness of this 3D shape prior. They remove the first stage and optimize from scratch, as table 1 shows. Optimizing without a 3D shape prior degrades the performance significantly. So, I mean, it's hard to say. This is kind of worthless. Like the Frechet inception distance as a kind of ablation. I think this is actually the one you want to use here. You actually want to qualitatively look at the images and see what the difference is. So This is the prior loss for the shape. So you can see that without the shape loss, you lose the back of the bench. But with the shape loss, you get the four corners of the bench, you get the back of the bench. So it really does seem like the biggest kind of performance improvements that they're getting with this paper compared to other works based on this ablation study is their shape prior. All right, limitations in future work. Our framework depends on fine-tuned stable diffusion model to synthesize style images to feed into the image-to-shape module. Despite the strong generation capability of stable diffusion, we cannot constrain it to avoid generating shape images that are out of distribution of the 3D shape generator. Yeah. Stable diffusion is trained on a mega-scale text-image dataset, while the 3D shape generator can only generate a limited amount of shapes, right? Only 13 categories in the ShapeNet dataset that they used. So we hope to introduce stronger 3D priors into our framework. Yeah, I wish someone used, what am I thinking? There is a way, like I feel like there's probably a strong 3D data set out there, especially in one of these like model, like Turbo Squid, right? Something like this. So Turbo Squid is like a 3D model marketplace where you can go and you can say, okay, free 3D models here, and these are all free, right? So you can go and you can buy this like pair of boots, right? So like these are boots that someone made, and this is a pretty high quality 3D object, right? So if someone took the time to make a script that could go and basically scrape something like Turbo Squid for every single 3D model that is free, and then turn that into a data set that you could use instead of ShapeNet, I think that would be a way to introduce stronger 3D priors into the framework. You could do basically a similar thing to what this paper is doing, but rather than just using ShapeNet, which is just like these kind of pictures of cars or these 3D models of cars and benches, you use something like 3D models here. So like, I don't know, animal, for example. Look at all these. Some of these are really good, you know, like look at this cat. That's a very, very nice cat, right? It even has like all the fur on it and the texture. Has good topography. So I think that's the next step to me if I was on this project. Okay, in this paper we present Dream3D. Our framework leverages text as shape synthesis. Present a simple yet effective approach that directly uses a fine-tuned text-to-image diffusion model. Cool. So let's scroll through here, see if there's anything interesting. The generative model here is Dolly 2. So they're using Stable Diffusion, Dolly 2, and Clip. This is the nerf that they're using, DVGO. Illustration on 3D optimization with a 3D shape prior. Visualize the contours of the density grid and the volume rendering images. 500, 5,000. So this is like at the very beginning of training and at the very end of training. So this is like this is actually almost bad, right? Because it's like, look at how much more noisy this gets. Cool. So I think we're gonna call it there. We're almost at the 2-hour mark here, but that was Dream3D, zero-shot text to 3D synthesis using 3D shape prior and text to image diffusion models. Interesting work coming out. I think tomorrow we're gonna look at the Google paper that came out, but I wanted to do this one beforehand. Yeah, thanks for watching. Thanks for listening. Thanks for